How the ridiculous design of the only German aircraft carrier and the policy of pauses in 1940/43 turned the Graf Zeppelin from a Plan Z dream into a laboratory corpse. Artillery instead of planes, trolleys instead of pace. The hum of the open hearth fades away, and the Kiel smells of wet steel and chalk markings. The engineer runs his palm along the frame of the future deck, and seems to hear the rumble of 200,000 powerful turbines, which do not yet exist. There are Plan Z signatures on the flagstones. Political posters show ocean grandeur, battleships silhouetted into the sunset. According to the schedule, this ship should be commissioned in the late 40s. According to the world calendar, 1938 is already underway. The lines between what is desired and what is possible diverge like isobaths on a storm map. Plan Z was born as an ambitious revenge geometry. By 1948, the Kriegsmarine was to transform from a coastal force into an ocean-going fleet facing the British Empire. The designers laid out the future power on the shelves. Battleships, heavy cruisers, aircraft carriers, auxiliary formations, docks, training centers, personnel. The point was strategically clear: to block London's commercial arteries and move the Royal Navy away from the European coast. The problem is with the watch. The fleet has been built for decades, not in speeches. Germany already started the war in 1939, like a student who showed up for an exam in quantum mechanics with a notebook on arithmetic. The Versailles restrictions created a paradox. Having lost large ships, the Reich retained the ability to build hulls and mechanisms, but lost the culture of ocean use. Battleships and cruisers can be overtaken by numbers and armor, but an aircraft carrier is not a tonnage, but an ecosystem. Carrier-based aviation, doctrine, training, emergency service, flight dispatching, communications, weather service, catapults, and aerial finishers, fuel and ammunition depots, hundreds of regulations. Plan Z ticked the box. Aircraft carriers, 4 units, but did not include an equivalent amount of time for growing people and procedures. As a result, by 1939 he was an avant-garde on paper, but in reality, he was a freshman. The second layer of inconsistency is economics. The industry, squeezed out by programs of land weapons, air defense and motorization, had to simultaneously feed the cathedral projects of the fleet. High-hardness armor, turbines, complex boilers, optics, radar. Each section of the aircraft carrier is a clock of machine time, which was desperately lacking for tank and artillery orders. Factories and shipyards were overloaded, deadlines tightened into an accordion. At the same time, the submarine fleet, cheaper and faster in production, promises instant returns. The inner choice between necessary yesterday and useful the day after tomorrow turned out to be a foregone conclusion. The third is an institutional conflict. Naval aviation in Germany was subordinate to the Luftwaffe. This means that the deck pilots, aircraft, and even the type of missions were determined not by the Navy, but by Göring's department. For an aircraft carrier, this is a deadly inconvenient bundle. The ship plans a cycle of sorties, but the resource and composition of the wing do not belong to it. In Anglo-Japanese logic, a ship is an instrument of aviation. In German, the ship remained a ship, and aviation was a borrowed option. This is how solutions like armored belt plus 150 mm artillery on an aircraft carrier were born. The ship wanted to live like an armored cruiser in an era where waves of planes were decisive. The fourth is a strategic confusion of goals. If the task is a trade war and disconnection of communications, the aircraft carrier must provide long-range reconnaissance, cover for raiders, attacks on convoys and supply bases. This requires a large, fast air group and a simple, reliable deck routine. The German design turned out to be a heavy hull with a moderate air group and technically sophisticated but capricious catapults. It looks like an attempt to solve two competing ideals at once: artillery duel and aircraft carrier maneuverability, and lose to both. The fifth is the war calendar. The Blitzkrieg in Poland, Norway, France, the Battle of Britain. All campaigns require immediate funds. The Bismarck experience has shown how expensive it is to go out alone without an air umbrella. But instead of the accelerated growth of carrier-based aviation, the country is moving to the underwater priority. In 1942, when they were trying to revive the project again, the United States and Japan had already lived the fiery semester of Coral Sea and Midway. Their aircraft carriers are not ships. but well-established flight conveyors. The Germans are still arguing about the composition of the wing and are redesigning the nose tip for seaworthiness. The gap turns into a chasm. The sixth is the lack of infrastructure and habitat. Bases, hangars, aviation warehouses, deck machinery repairs, schools for navigators and signalmen are the invisible half of the aircraft carrier business. Plan Z built giants, but did not create ecosystems around them at the right pace. Even if the Corps had been brought up to readiness in 1941, 1942, it would have taken months, if not years, to train the crew and fly tactics. War, on the other hand, does not issue deferrals for a complex object for a good reason. In sum, Plan Z has become astronomy without a telescope, beautiful orbits on Wattman, and an unprepared sky in reality. He sincerely aspired to sea power but laid it in the future, which did not come. When the starting pistol of 1939 went off, the runners were already standing on other tracks. The aircraft carrier as a class required a cultural revolution within the Navy and interagency peace. Germany opted for mirrored armor and an underwater whip. Graf Zeppelin was born on a time loop between two epochs and remained the mark of the compass in the drawing. In the next chapter, we'll look at how this time loop materialized in iron, from the armored belt to the bulbous sides and 6-inch casemates. When the Graf Zeppelin was designed, the character of a heavy cruiser was placed in the heart of the aircraft carrier. The symbol of this dual nature is a battery of 16 150mm guns in casemates along the sides. For a ship whose strength should be measured by the number of aircraft in the air, such a decision looks anachronistic, but the logic of the designers is visible. Meetings with cover destroyers, night battles in narrow spaces, and shelling of coastal targets during raiding operations were expected. The 6-inch gave confidence and self-sufficiency without regard to aviation, especially with a shortage of deck torpedo bombers. The price is tonnage, people, sellers, bulky energy for supplying ammunition, and most importantly, volume and weight. Moving away from the main task, lifting and receiving aircraft. A casemate is a low, partially built-in accommodation. On a high-speed large hull, this meant wet positions, especially during the northern unrest. The wave floods the embrasures, sealing, shields, pumping are required. Each gun, along with a cellar, a feeding machine, armored shields, and a crew, turns into a local fortress sticking out in the area where elevators and hangars were installed for aircraft carriers of other countries. The cellars take the cubic capacity from the aircraft depots, and the ammunition elevators pierce the floors where the taxiway and communications of the deck crew would be better. Add smoke and shock waves of gunfire. On the open flight deck, this is not only noise, but also a real threat to refueled vehicles waiting for the catapult to be pushed. Above the 6-inch guns towered the universal air defense, 105mm, 37mm, 20mm. It was necessary and logical, but in total, the artillery industry grew so much that the ship began to resemble a hybrid of a battle cruiser and an aircraft carrier. Where the British or Americans saved every kilogram for the sake of additional aircraft and fuel for them, the Germans put another barrel and another armored tank. The paradox is that the stronger a ship is in the artillery sense, the smaller it is in fact an aircraft carrier. The armor scheme continued the same, "I'll take the hit myself" philosophy. The flight deck received steel sheets of considerable thickness. The main armored deck was below. A belt covered the sides, and anti-torpedo bulkheads were inside. The idea is clear. Survive the hits, keep up speed, and launch a new wave. But armor is not magic. It's physics. The sheets raise the center of gravity, impair stability, require set reinforcements, and every millimeter turns into tens of tons that need to be dispersed and steamed. A heavy top is moody in a storm. It is harder for airplanes to brake on a hard deck. Any deformation upon impact affects the mechanics of the finishers and catapults. By 1942, engineers recognized what was evident in the stability test assessments. The hull requires on-board bulbous external outriggers along the waterline. Formally, this is both an anti-torpedo measure and a cure for stability. In fact, it's a compromise at a late stage of the project. The bulbs increase the width, reduce the draft per unit displacement, reduce the side pitching, and provide additional volume to absorb the blast wave. But the extra areas of the wetted surface increase resistance. Visibility also increases. Circulation characteristics change, which means that the flight deck operates in the wind. Any patch on the hull responds to the schedule of takeoffs and landings. The result is an architecture with conflicting priorities. Artillery requires a low, dry side and rigid mounting points. Armor requires solid contours and mass where an aircraft carrier should have voids for damage control and aviation communications. The aircraft carrier, on the contrary, likes a high and dry deck, spacious hangars, free corridors for people and compressed air, and the simplest possible connection between fuel depots and refueling posts. The German project tried to sit on two chairs at once and naturally sank in both. The air group turned out to be small for such a displacement, and the cruising self-defense did not turn the ship into an unsinkable bastion. Proponents of the concept retorted. They say, a single raider in the North Atlantic should fend off the enemy's light forces and live under the attack of aviation. The counter-argument of the practice sounded different. A single aircraft carrier without powerful carrier-based aircraft is easy prey when encountering a compound, and is helpless if it cannot quickly raise, deploy, and return a large wave. Then every ton invested in the 6-inch jacket and armor takes away the chance for a second strike group. The extra minutes of reloading catapults and running around the flooded deck are more important than the thickness of the belt. The bulbs have become a visual marker of a delayed correction of the exchange rate. Instead of reassembling the concept for a flying conveyor, the project was reinforced with plates on an already established frame. From an engineering point of view, this is a beautiful, difficult, and decent job. There is an alarming signal from the operational side. The ship outweighs the cruising side, precisely when the squadrons and their turnover rate decide the world. In the next chapter, it will be seen how the composition of the air group, from the FI-167 to the carrier, based BF-109T and Ju-87C, finally fixed this duality and turned the soul of the artillery ship into the brake of the aircraft. The first sketch of the air group looked almost idyllic. The FI-167 torpedo scout, the Ju-87C dive bomber, and the BF-109T fighter. The paper provided a harmony of roles: search, strike, cover. Reality has brought together three different engineering worlds on deck, where the most important modes of takeoff and landing, the speed of turnover of departures, and survivability in the marine environment. This is how the Frankenstein Air Group appeared, a set of incompatible habits and technical compromises. The FI-167 was the best candidate for marine rough work. A two-seat biplane with excellent takeoff and landing qualities, and a short takeoff, could land on the deck almost on foot and take off into the air from a short track without asking for full head from the catapults. He carried a torpedo or bombs, carried out reconnaissance and fire correction. In the North Atlantic, such a flying boat without a boat bottom would help both in searching for convoys and in launching an attack. But bureaucracy and changed priorities did their job. The classic deck torpedo bomber did not fit into the tastes of the Luftwaffe. The biplane looked outdated, and the land speeds beckoned. The FI-167 was left behind, along with part of the deck logic. Without a reliable torpedo bomber, the aircraft carrier lost its long arm against ships. The rate has shifted to strengthening the diving component, the Ju-87C. The platform is familiar, the impact is reliable, and the accuracy is high. It was adapted for the sea. A reinforced fuselage, catapult mounts, an aerial finisher hook, and buoyancy aids for accidents on the water. But the dive bomber is a tool for weather and time of day. His short legs limited the radius, and the assault profile required close training and a calm horizon. In the role of a universal hammer, the Ju-87C overloaded the flight deck economy. More maintenance cycles, complex suspension, increased vulnerability on the way back without cover. In addition, he did not cover the tasks of long-range reconnaissance, anti-submarine patrol, and night watch. The BF-109T, a rare deck-based version of the famous fighter, hung on the cover. For the sake of the sea, they extended the wing and strengthened the mechanization, installed a boom, and added ejection locks. Speed and vertical are strengths, but the hereditary disease remained. The narrow landing gear track punished the slightest mistake on a wet deck. Landing speed and stall behavior required jewelry. The navigation resource and range are modest. The towing radius of the cover is small. As a result, the fighter was suitable for a short canopy above the warrant, but it quickly ate up fuel and forced them to save on maneuvers. Bad news for deck air battles. The design eclecticism was compounded by the deck infrastructure. German catapults with trolleys promised a quick salvo of the first wave, and then a long pause to recharge and return the trolleys. The layout, where gas receivers and compressed air routes ran close to the flight zone, made the system vulnerable to splinters and fire. This was critical for a diverse air group. Dive bombers and fighters required different preparation and launch rates, and the torpedo bomber, which no longer existed, had its own safety regulations. Any delay or micro-damage to the infrastructure tightened the pace to the level of 1 attempt per hour, whereas a successful aircraft carrier war is based on high-speed turnover. An institutional one was added to the cultural seams. Pilots and materiel were subordinate to the Luftwaffe, the ship to the fleet. This influenced the preparation. Deck landing is a craft developed by hundreds of touches, simulators, routine night landings, lighting services, and signalmen. Where the British and Americans had been building schools and procedures for years, the Germans were trying to transplant land habits onto a slippery floor. The breakdown, the lateral catch, the rebound from the cables, all this was solved not by a slogan, but by a raid. A raid is kerosene, a motor resource, a chain of service specialties that they did not have time to learn in the right amount. Another layer is suspension logistics. A dive strike is good against stationary targets and ships caught without advanced air defense. But against a convoy under the cover of fighters, a combination is needed. Reconnaissance guidance and a massive torpedo salvo from different courses. Without a torpedo bomber, an aircraft carrier is forced to either strike in small portions or risk diving in a zone of dense fire. Even if experienced crews had appeared, the wing's composition pushed tactics into a narrow corridor of solutions. When the project was revived in 1942, the world of aircraft carriers had already learned the lessons of the Coral Sea and Midway. Only the air group that combines range, rotation, and a steady pace of takeoffs and landings is viable. By this time, Graf Zeppelin bore traces of all previous tosses. The torpedo bomber disappeared. The dive bomber became the main hammer. The fighter was a compromise between the deck and the land pedigree. It turned out to be a set of parts that worked separately, but together prevented each other from opening up. In the end, the air group looked impressive on the poster and clumsy in the flight schedule. She lacked a long-range eye, a long torpedo arm, and deck routine. The machines required different start, up, and maintenance modes, and the deck required one, a seamless conveyor. The Frankenstein came to life in spurts and froze after the first impact, leaving the ship with an empty deck and a long pause. In the next chapter, we'll look at how catapult trucks and the layout of gas systems transformed these pauses from a design detail into a strategic problem. In the drawings of the Graf Zeppelin, the ejection system looked like a futuristic attraction. 2 parallel tracks along the bow, batteries of compressed air receivers under the deck, and launch trolleys at the top, on which the entire aircraft was placed. The machine was fixed by the power units. The mechanics connected the pneumatic lines. The calculation entered the launch parameters, and at the signal, the trolley took the plane to the edge of the deck with a sharp, almost shockless jerk. The first act of the performance was dazzlingly fast. A series of launches went on almost by stopwatch, wave after wave, as if the deck had turned into a conveyor belt. And it was this brilliance that hid the main defect, everything that happened after. To make cart magic work, the ship dragged with it a complex organism of pipes, valves, pressure gauges, and high-pressure manifolds. The receivers pumped air to impressive values, distributed it along both ejection lines, and gave an impulse to launch through the metering units. But the physics of compressed gases does not like infinity. The supply of impulses is finite, and recharging requires time, energy, stable operation of compressors, and silence around vulnerable units. The German calculation honestly envisaged a salvo first wave, after which the system entered the mode of long, nervous breathing. The battle rhythm was breaking down. After a brilliant start, an interact came, in which the deck turned into a workshop for restoring its own capabilities. The trolleys added a second deceleration loop. Each one, having worked out the launch, went over the side edge and had to return to its starting position along the guides and return paths. It seemed like nothing on the diagram and turned into a choreography of risks in reality. Wet steel, salt spray, tremors from waves, small debris capable of clogging rollers. Any delay with one cart blocked the track, and the track, which was under repair, cut the pace of departures in half. The compromise of a complex mechanism for the sake of a beautiful start pace turned into a slow, viscous return time to the next wave. The vulnerability of the infrastructure increased the drama. Receivers and highways located close to the flight area lived under the threat of debris and fire. Fragmentation due from close ruptures, which for an ordinary deck often means a local hole and a couple of hours of rivets, could become a systemic accident for the gas system. Depressurization, pressure surges, uncontrolled discharge, a ban on, starting until a full check. The fire danger was two-sided. The compressed device itself does not burn, but hot metal, oil, paint, cables burn perfectly. And pneumatic pipelines like to pull out fasteners and destroy partitions if they are driven by temperature. Where the Americans and Japanese needed to inspect the cable and brake drums, the Germans needed to inspect the entire lung system of the ship. The deck routine suffered from technological exoticism. The takeoff cycle should be monotonous, like a metronome. Rollout, refueling, suspension, launch, takeoff or ejection, recruitment, clearing positions for the next one. The cart scheme broke the monotony. The aircraft was first moved onto a trolley, fixed, the attachment points were checked, and the operation with the metering valve was synchronized. After launch, the deck crew was distracted by the logistics of returning trolleys and maintaining the line, instead of dealing with the flow of cars. Any additional step in the chain means extra minutes, and minutes on an aircraft carrier are more expensive than millimeters of armor. Another shadow is atmospheric. Pneumatics are susceptible to temperature and humidity. Salt water and condensate are the enemies of valves and seals. In a storm, the compressors live at their limit, under a jerky load. In frost, the seals turn brown, and the calculated pulse schedules go haywire. A good mechanical ejection plan turned into a climatically capricious device. When the simultaneous rise of the fighter cover and the strike group was at stake, a climatic whim could disrupt the connection. The fighters were already in the air. The dive bombers were waiting for the main line to recharge. The cover was melting by the minute. This is not to say that German engineering underestimated the risks. On the contrary, the system was thought out, had understudies, bypass valves, and emergency shutdown procedures. But simplicity wins in war. The American run-up, with short hydro-pneumatic catapults in case of overload, and the Japanese emphasis on clean taxiing and precise work against the wind, ensured the main thing, the predictability of the rhythm. The German bet on a technological leap, gave a flash of efficiency, and then dragged along a trail of regulations. Tactics also rested on mechanics. The salvo, first wave, tempted to plan a decisive blow in one fell swoop. However, after launch, the deck became vulnerable. Some of the planes were in the air. The cover was limited by the radius, and there were no reserves for a quick second wave. The enemy, having survived the initial blow, received a window for a counterattack on a ship with an empty deck and tired pneumatics. The choice between a strong start and a steady pace was always decided in favor of the latter. The German scheme pushed for the former. Finally, resource intensity. Catapult trucks required trained teams, stocks of gaskets, valves, lubricants, and regular inspections. Every minute of the engineer at the catapult is a minus minute for the technical staff of the aircraft. In an environment where the air group is already small, human resources are becoming no less scarce than steam and steel. The more complex the launch architecture, the less attention is paid to what really turns an aircraft carrier into a weapon: the turnover of flights. The Graf Zeppelin catapults are a perfect example of engineering perfectionism, designed for the perfect day and perfect routines. Naval warfare does not indulge in ideal days. Mechanisms that tolerate dirt, rain, splinters, and human fatigue are appreciated there. The German system brilliantly illustrated how the technological spectacle suppresses the craft of the flight deck. In the next chapter, we'll see how the political decisions of 1940 and 1943 finally sealed this gap between design and combat reality, halting work precisely when the project needed a ruthless, simplified reassembly. In the spring of 1940, the Graf Zeppelin stood on the slipway like a promise about to be fulfilled. The flight deck loomed, the ejection lines assembled. The mechanics argued about adjustments, but Berlin has set priorities differently. The meeting with Hitler transferred resources to the here and now. Norway, coastal batteries, protection of ore convoys. At one point, the ship, conceived as a symbol of the future fleet, turned into an iron donor. The 6-inch guns were removed and sent to the fjord fortresses, anti-aircraft installations. This pause was a cross-section of the entire early campaign. Plan Z lived on the horizons of 1948, and reality demanded immediate action tools. The shipyards asked for months, the front demanded a day. The industry, already overloaded with land orders, could not simultaneously pull a complex aircraft carrier, tanks, air defense, and a submarine fleet. Each ton of high-quality deck armor matched the armored decks of Norwegian batteries. Each electric motor of the elevator matched the contacts of searchlights and radio stations. In such arithmetic, the aircraft carrier naturally lost. It gave a perspective, but it did not give a tomorrow. The political decision of 1940 consolidated the doctrinal shift. The picture of the fighting pushed for asymmetry. The submarine trade war promised rapid and measurable pressure on Britain. Dönitz justified this with tables of tonnage losses. Raeder defended the surface force, but found fewer and fewer allies in the resource headquarters. One unfinished aircraft carrier without schools, airfields, and pilots was losing out to a dozen. U-boats that could be mass-produced tomorrow. For the first time, Graf Zeppelin turned from a bet on the future into a spare parts warehouse for the present. However, in 1942, the project was revived. On paper, it looked like a rational revision. Onboard bulges for stability, bow changes for the northern seas, air defense adjustments, fuel and ammunition storage refinement. The plan was simple. Take the ship to the Baltic, put it on a training pendulum, and work out a deck routine. But the world of aircraft carriers has already moved forward. After Coral Sea and Midway, it became clear that the value was in pace and unification, in a large air group and simple procedures. The German project continued to believe in armor and sophisticated catapults, arguing with the very logic of the flying conveyor. Meanwhile, each week of delays stretched into months of backlogs. A new political shadow has fallen over all this. The experience of the Bismarck and Scharnhorst, raids on bases and fuel shortages undermined Hitler's faith in big ships. In the winter of 1942-1943, confidence finally shifted to submarine warfare. The January castling, the departure of Raeder and the arrival of Dönitz, fixed the course. The formula, large surface ships are no longer needed, sounded like a verdict for Graf Zeppelin. In January 1943, the work was stopped. The second stop turned out to be different in nature. If in 1940 the ship could still be unfrozen, then in 1943, the rule of irreversibility began to apply. Suppliers curtailed unique orders, specialists moved to other programs, and the removed equipment was distributed to coastal facilities. The hull was driven between Kiel and Stettin, hiding from enemy airstrikes. Each move meant months of downtime, new corrosion, and a new fit. Any deck system loves continuity. Elevators, catapults, fuel lines, and aerial finisher cables are the worst at taking pauses. In practice, it looked like the project was bursting at the seams, not from the impact of bombs, but from the slow chemistry of time. Meanwhile, the economy has finally voted for the wolf packs. Financing, fuel, machine time. Everything flowed to where the reporting figures of the sunk gross register tons promised. The aircraft carrier could not give such figures, at least because it would require another year of training and a separate culture. Propaganda didn't help either. A country that lived by Sagodnia's reports needed a visible result, not a dull bulk at the pier. This is how political logic converged with production logic, and Graf Zeppelin turned into an expensive but tacit metaphor for lost time. Was there a third way? Theoretically, yes. A radical reassembly. Remove the 6-inch plates, lighten the armor, simplify the catapults, expand the hangars, get the air group to a volume corresponding to the displacement, and at the same time, create their own naval aviation outside the care of the Luftwaffe. Practically, there was no more time. By 1943, the Allies had built up escort aircraft carriers, radars, and air defense systems, and the skies over the Baltic and the North Sea were becoming less hospitable. Any insistence on completion rested on a shortage of fuel, aluminum, experienced pilots, and quiet shipyards. It is useful to consider both stops as a mirror of the project's systemic contradictions. The 1940 decision showed that an aircraft carrier without institutional support, when the Luftwaffe has planes and pilots, and the Navy has a ship, inevitably becomes a political toy. The 1943 decision proved that a hybrid with an artillery soul cannot withstand a collision with the economy of total war. Politics didn't just take away Graf Zeppelin's chance. It delivered a verdict on the very philosophy of armor plus trucks, where pace and simplicity were sacrificed by the appearance of self-sufficiency. The ending is obvious. In the spring of 1945, the hull will be flooded during withdrawal. A year later, it will be raised by Soviet specialists, and in 1947, it will be tested for damage resistance. But that's another scene. Here, in 1940 and 1943, politics changed the watch at the helm and turned off the Dream engine. The aircraft carrier was left without a deck, not because it could not be built, but because there was nowhere and no time to grow it. In documentary optics, this is more important than any millimeters of armor. The fate of complex machines is decided not only by drawings and metal. The result of the pauses is simple. The dream of the Navy of the future has given way to the arithmetic of war. In the spring of 1945, the Graf Zeppelin's hull stood at the mouth of the Oder River like an empty stage after a hastily disrupted performance. The Germans sank the ship during departure so that it would not reach the enemy alive. The water lay on the deck, skewed the bulkheads, extinguished the remains of the cables. A year later, other people turned on the lights on this stage. Soviet engineers examined the hull, pumped it out, repaired the holes, lifted it and towed it to the Baltic. What's next is not the completion, and not the museum. He was appointed to the role of a rare but necessary actor for military science. A big target, for complex tests of damaging factors on a large ship. The summer program of 1947 was not like a movie. Dry magazines, explosive consumption, trajectories, damage tables, artillery, bombs, then torpedoes and internal explosions worked on the hull. The scenarios were applied, not to sink at any cost, but to understand how such a mass of steel holds up under successive blows, what happens to the longitudinal strength when the flight deck collapses, how the highways behave when fire and water cross. Engineers measured deformations, entered them into diagrams, photographed seams where metal bloomed from old floods, and places where new explosions tore off the skin, exposing the power set. It was not an execution, but a laboratory. Tough, but extremely pragmatic. To find out what the armored philosophy of a heavy aircraft carrier is worth when it is operated from both air and water. The final scene occurred on August 16, 1947. After a series of defeats, the ship lost stability. In the end, torpedoes were fired at it, and the hull lay on the bottom north of the Polish coast. The coordinates and details remained closed for a long time. The war had just ended. A new era of secrets was beginning in Europe, and reports on the testing of large-scale targets were moving into classified sections. To the outside world, the aircraft carrier dissolved. Formally, lost during towing. In fact, it became a reference record in the test reports. Where there are no documents, legends grow. In post-war mythology, Graf Zeppelin turned into a brass safe with Baltic jewels, a flying garage with unique aircraft in hangars, or a floating laboratory of secret radars. He was credited with escaping from the impact in storms. Other places of death were named, and they argued about the method of diving. The story of mystery lovers was pushing for romance. An untouchable steel bulk, night tugs, silent pilots, archives under lock and key. And the further the 1940s went, the more willing the stories were to juggle, maybe, and say. Meanwhile, the practical side of the afterlife was working in silence. Test reports were read by designers and gunners. The conclusions spread to the departments of shipbuilding and headquarters, where they counted how many bombs in what sequence and at what angles the guaranteed failure of the power set would give. For a researcher of Baltic storms, this was a rare opportunity to see how a large hull dies not from a single, magic bullet, but from a chain of factors. How water is carried through the compartments, and how slowly but inexorably buoyancy is lost as a result of constructive fatigue. In the 21st century, the whisper of legend has been replaced by an echo sounder. In the summer of 2006, Polish hydrographers discovered a distinctive silhouette at depth. A long hull with a destroyed flight deck, sinkholes in the bow and traces of late explosions. At first there were neat, maybe shots. Then there were shots that revealed the contours of the hangar and the chipped ejection lines. Military experts have confirmed, it's him. The point on the map is located about 55 kilometers north of Władysławowo. The depth is such that no one goes there for amateur diving, and professionals rarely and cautiously descend. On the sonar screen, the ship looked like a half-forgotten blueprint returned from the archive, still readable, but with gnawed corners. This discovery quickly dismantled the myths into details. There could be no squadrons in the hangar or fabulous treasures there. The trials of 1947 left what needed to be left for the technique and destroyed the rest. But something else became visible. The true teleology of the project. The images showed a rigid, heavy flight deck, torn apart by sections. Powerful bulkheads that resisted and then surrendered. Characteristic elements of the ejection system with a cart philosophy. Even lying at the bottom, the ship confirmed the diagnosis. It was built as a self-protected aircraft carrier, where mass and complexity cover a modest aviation potential. The Baltic, devoid of pathos, confirmed what the dry tables said about it. The mythological trail, however, has not disappeared. Any major find leads to a second life. A life of reconstructions, documentaries, and virtual models. A calm, almost archival romance was born around the Graf Zeppelin. Coastal museums included its plans and exhibitions. Artists began to draw what it could be like in service. Engineers argued about whether it would have been possible to make a flying factory out of it if they had chosen a different path in 1940. But now it's no longer about a miracle, but about the price of time and priorities. The medal on the bottom doesn't argue. It reminds. This concludes the posthumous biography of a ship that did not have time to be born as a fighter, but proved useful as a teacher. The trials of 1947 moved him from the category of failed to the transferred to experience section. On board, they measured how large ships break down and hold on, and the discovery of 2006 returned his name without speculation, attaching the coordinates to the legend and making the hearing a subject of study. For a documentary article, this is an important twist. Instead of the sad, not built, the pragmatic, helped to understand, appears. The Graf Zeppelin did not become a weapon of the Navy, but it became part of the knowledge of the war at sea. And perhaps, this is a rare form of posthumous justice for a steel ship.